Okay, so in the last class, so we were discussing about the geometric optics, how you can use Fermat's principle to describe reflection and refraction and so on. And there is another part which we will be mostly covering in this course is the wave optics. And we also discussed that a generic mathematical expression you can write to represent your propagation of wave as a function of position and time, or how it propagates in space and time. And in three dimension, so you write it down as del square psi is equal to 1 by v square del square psi by del t square. So the left hand side represents how the wave propagates in space. Your del square is your del square by del x square. So these are all partial derivatives. And v is your velocity, which is also related to your permittivity and permeability of the material in this. So if it is, so not in general, so I am talking about velocity v. If we say it is not v, but not like that, but later on. So v is velocity, and the right hand side is the how the wave propagates as a function of time. Now the solution, a general solution that works to describe this propagation, so you can write as with some amplitude a, and then so cosine k x or kr. So because we are writing in three dimension, so it is k dot r minus omega t. So plus or minus both will work, and then with some phase factor. Okay, so this is a very general solution. So even normally the solution you write as a complex one. So instead of this cosine one, this function will also work, where you are writing it as a cosine, exponential function. So this is also a solution to this wave equation, where a is your amplitude, and what is k? K is your wave vector, which is given by 2 pi by lambda. So if you substitute that, you also get your familiar expression of so, and omega is will be equal to omega square will be equal to k square v square. Okay, or this is equal to your 2 pi mu whole square. So if you substitute that, you will also get your familiar expression in terms of x minus vt or x plus minus vt, that expression that you use. So 2 pi by lambda by x minus or r minus vt plus minus vt plus pi. That expression you'll also get when you substitute this. So in case of electromagnetic wave, this velocity v is your nothing but velocity of light, which is given by this, will be related to your permittivity and permeability in free space in this expression. So I think you have this relation as well from the electromagnetic theory.
Yes, sir.
So now the most interesting thing happens when these wave, so in context of optics, when these waves they meet some obstacle, or a different medium, or in a way, not only different medium, but some slits or holes in particular. So how that changes the behavior of the wave. So we will look at that. So originally this wave theory was developed by Huygens. So in English it is Huygens, but actually he was a Dutch physicist, and the pronunciation is very difficult. It's Huygens, okay, Huygens principle. Uh, but the name, uh, whatever is easier for you, you use that. But the principle remains the same. So what he assumed that so before that it was all about geometrical optics. So people were not discussing about the wave nature and how to use that for explaining some of the phenomena. So what he suggested, so this is, we say, Huygens principle. So he basically, he's known as the who established the wave theory of light. So what, in a nutshell, I can say that if you have, this is, you are representing your wave, then what he suggested, so you can represent these waves as something like wave fronts. So the propagation is nothing but the propagation of the wave front. And again, these wave fronts are basically perpendicular to your this propagation direction here. So if the propagation is along this direction, so these are the wave fronts. This is how they move. And each point on this wave front acts like a spherical wave. Okay, so each point on this wave front, so how the wave moves forward, it is because each point on the wave front acts like a spherical wave. Okay, and this is how the wave propagates forward. Okay, so this is what his principle was based on, and which worked really well to explain one of the most famous experiment in physics, which is the Young's double slit experiment. So what is Young's double slit experiment? So this is, zoom in a bit. Okay. So what Young did this experiment, he took a source of light, monochromatic light, sodium lamp or mercury lamp, vapor lamp, and then you shine it on two slits, S1 and S2. So through a pinhole, the light passes through a pinhole, and then he put it or exposed two other pinholes, S1 and S2, which are separated by a distance d, and on a photographic plate which is at a further distance capital D. So he observed this fringes. So fringes means, so you have alternate bright and dark straight lines, so to say, on the screen. And this is known as the interference. So I think I suggest that you don't discuss or chat about anything else other than if you have any question in the chat box. Okay. So if you have any question, put it in the chat box. Otherwise, don't put any general comment there. So these dark and bright fringes, this pattern is known as the interference pattern. And so you have alternate dark and bright fringes, which we call as a constructive interference and destructive interference. So you have, where you have the bright fringes, you have a constructive interference, and if you have a dark, so this is a destructive interference. So what a constructive and destructive interference means, if you look at the wave picture, so you can say that you have a source here which is giving rise to this spherical waves, and then these wave fronts, when they move, so normally you assume the source is far away from your slits S1 and S2, and you probably would have a plane wave front, but that also doesn't matter whether the wave front is plane or spherical. So irrespective of that, you will get an interference. So at the source, so each slits that you this wave fronts encounter, so they will act as a source itself of spherical waves, and now these two spherical waves S1 and S2, so they will interfere with each other. Okay, and now if you look at the wave picture, so you can see the central part here. So just this, so I'll draw the line here. So this is, if I draw the line here, so you see the waves are in phase, and that means the crest is at the crest, so both the waves, the crest at the same position, and therefore they interfere constructively, or you can say there is a superposition of the displacement which you just add up. Okay, so due to this you just add up the displacements, and therefore you have the amplitude becomes more, and that's why the intensity is higher. So you have a bright you see a bright light at that, in that direction. Now if I take another direction, let's say, so let me draw that. So if I draw this direction here, in this direction also there is a addition of the displacements, and the waves are in phase. Okay, so that means crest meets crest and trough meets trough. So therefore you have a constructive interference, and you see a light or a bright spot on the screen. Now similarly on the other side, so let me draw that on the other side of the, in this direction. So again, this is the same thing is happening. So you see a light or a bright fringe there. But in between that, you have a situation where the phase difference between the waves, two waves, are exactly opposite. So therefore, if there is a crest for one wave, for the other wave there is a trough. So that means if the displacement is positive, for the other wave the displacement is a negative direction. And when they meet, so that means they're in the opposite, the phase is exactly opposite, and that's why when they meet, so there will be no light, or the light will be really small, and that gives rise to a dark fringe. So that is how you create this alternate light and dark fringes due to interference. Okay, so this is a beautiful experiment in physics which is very universal for all kinds of waves. So you can observe this not only for light, although Young's experiment was performed on light, so you can perform it on so water wave, also shows that
Sound waves also, sir.
sound waves as well. In fact, electrons, protons, neutrons, which are quantum mechanical particles, so they also show this interference pattern as well. So if you take even electron and do this double slit experiment, so you will observe also a interference pattern. Okay, and that actually one of the demonstration which showed the wave nature of electron, which was so de Broglie proposed that electron matter can behave as a wave in quantum mechanics, and it was shown by so it was proved because of this interference. The electron showed interference when this kind of experiments were performed. So this is like one of the very basic experiment, which is also very one of the universal experiments brilliantly done by Young. So what is so unique about this experiment is this this is possible. So if you take so let's say if I take two different sources here, so S1 and S2, so if I instead of taking the same wave, so let's say I put a source S1, so I put one lamp here, another lamp, a second lamp here at S2. So will I observe an interference pattern? So both are different. So let's say assume they are both wavelength same. So lambda is same for both, but they are completely different sources. So they are not coming from the same source. So it is a lamp 1. I'm putting a sodium vapor lamp 1, another sodium vapor lamp 2, and now I do this experiment. So do you think there will be a interference?
So there will be, but it will not sustain interference, I think.
So the phase will be different, so there is no possibility of
So what do
Means
you
interference.
mean by not
up
sustained interference?
means
Sir, no interference
the position of maximum or
because
minimum will not remain at that
sir,
position. It will keep on shifting.
So we
Shifting.
won't get that slits line. We will get something else.
You will
So
get
the
sir,
position of light fringe and dark fringe are
Sir,
different.
coherent sources are not there.
So there will be
so there
interference,
are
but
many
it will not be
possibilities. Yes.
consistent. Means it will keep on changing. A position of maximum will keep on shifting from one position to other. It will not be persistent.
So why? What is the time scale of this change? So how fast it will change?
sir, there will be no interference because the light are incoherent.
Incoherent. Okay. Yes, that is another interesting point. So why light are incoherent?
Sir, the
Sir,
angular
because there is
frequency
some phase difference there.
and
We
constant
cannot
difference,
match the phases here.
Not the phases. Okay.
phase
Yes.
difference.
Sir,
Yes.
sir, there are two different sources.
Two different. Sorry again. Can you answer again? It was who was it?
So in
Azhar.
those two,
Yes.
so in the two sources, the light will come due to the de-excitation of electrons. So we cannot
Mm-hmm.
make sure that the de-excitations are exactly at the same time. That is why
Yes.
they will be out of phase.
Mm-hmm. Yes. So normally we will not observe really the interference pattern uh, because this is an incoherent source. And why they are incoherent? Because so coherence, for coherence you need that so one thing is
Phase difference
for
produced by them is constant.
yes, so the for interference to happen, the source should be coherent.
Coherent.
Yes. So coherent means there must be a constant phase difference, or there should be a relation between the phases should be well defined. If the phases are not
Both
that
should have
relation are
both
not
should have same frequency, na sir.
Yes, yes. I mean, lambda, I am saying that the both, I am using a vapor lamp, sodium vapor lamp. So lambda is same for both. Okay, so some students said, so few of you
Yes,
said
sir.
there will be interference.
Yes, sir, there should be interference, but it is not.
Yes, sir.
I think that there should be interference. There is nothing like that condition that only coherent sources can interfere. It's like that's a key. If coherent sources interfere, they produce constant phase difference. They have constant phase difference, so they have their position of maximum minima does not change. But it's not like that. If there is not coherent sources, they will not interfere.
So how then? So if you are saying you will see, so if you are saying if you put sunlight, so you will observe a interference pattern.
Maybe yes.
Maybe yes. Okay, so still.
Sir,
The position of the
So
maxima and
we
minima
will
will
observe.
change.
sir, it
The
will
positions will be
change.
different for different colors. Like for example, if the blue and the rest of the wavelengths are undergoing a maxima, might be possible the red and the other
Yes.
wavelengths are going under a minima. So we won't be able to get a different, a particular range of maxima or minima of the white light. It will be instead, depending on the colors, it will be a maxima or minima.
Yeah. Okay, so there are many possibilities. So when if you are saying you can see interference pattern, actually it would produce. So let's say, so when you have so how the light is produced. So this is due to the de-excitation of your electron. So now, if I am using two different lamps, so this process is it's really random. Now, if I observe, if I when I am observing with my eye, and normally you can observe a light for a certain average time. So if something changes, any phenomenon that changes beyond that time, so let's say I can observe for maybe a millisecond. Okay, so the change which occurs in millisecond, I can notice that. But if a change occurs uh, below a millisecond range, so that effect I cannot observe. Okay, so this process, if I am taking two different lamps and I assume that this transition taking place, electron transition happens, and there is a light comes out. So that happens in the time scale is about a nanosecond. Okay, so 10 nanoseconds in that range. And then those light, they might interfere, but with your eyes you will not able to see it, because that process, because the interference pattern will change in few nanoseconds, and your eye is not able to capture that change, and for you it would look like it is a uniform illumination, so you will not see any interference. But if you have a very fast camera, really fast, so you might see the interference pattern. Okay, which is able to observe this change in nanosecond range. Okay, but in general, when we say a wave, but still the light which are interfering, so they should be interfering when there is a very unique or the relationship between the phases is well known, well defined. Otherwise, they will never interfere. So, an incoherent source, irrespective of whatever the time, any incoherent source, they will never interfere. Okay, so it has to be coherent. So, okay, is it clear?
So, sir, when the source is sunlight, when the source is sun, then we can say that the interference patterns will be formed.
So I think sir, incoherent sources also interfere sometimes, because sir, we also have the formula of
No, you have
for
to make them coherent.
incoherent sources.
You have to make them coherent. So otherwise, you cannot do that.
It's we have a formula, sir. I average equals to I1 plus I2 for incoherent sources.
I1 plus I2.
for incoherent sources. The intensities just gets added up for
Yeah,
incoherent
but you
sources.
will not see this fringes. So will you
Yeah,
observe
that
this?
may be.
So you will not observe this interference, this fringes, dark and bright. So
Okay.
they will add up, yes. On a screen, they will add up. So you will have a
So,
uniform illumination, but
so
you
is
will
it
not see
necessary,
this.
sir, whenever light interfere, there must be fringes?
Yes, that is what interference means. So
Okay.
if you have an interference means you have a constructive and destructive fringes that a pattern you will observe. Otherwise, you will not say it is an interference. It is just
Okay.
the amplitudes just add up or the intensities just add up. So if I put two light bulbs in a room, so I'm not going to observe any interference pattern. It will just illuminate, it will make the room brighter because the intensities are adding up,
Yes.
but I will not see any interference there.
So, in case of sunlight, we can say that we are using a single source, so we will observe interference pattern, right? Just like rainbow colored pattern of all different colors spaced apart.
Mhm. Yes, but then you have to put it through a pinhole, right? You normally when you do the experiment, so you have to make a dark room. You have to pass sunlight through a very small hole, okay, and then you have to repeat a experiment something like this. So first you have to put a source, a pinhole here like this, where through which the sunlight should come in, and then you put these slits, and then you observe you can see the interference pattern. But it will be very uh, so. So sunlight consists of all different colors, so it is not a monochromatic light, and therefore each color will interfere, and the fringes uh, so what you will observe is a central bright fringe that you will observe, so maybe a little bit of dark fringes around it, and then maybe some a big little bit of color fringes, but after that again you will see actually a uniform illumination. So you will not see this clear dark bright fringes for extended region. So that is the problem with sunlight.
Sir, for interference, it's a necessary condition. We should get a pattern.
Yes, we should have this constructive, I mean this fringe pattern that we should get. So that is when we will tell this there is an interference. Otherwise, not. Okay, so so one thing is the source needs to be coherent, and one thing which also we say when interference happens, we say it is a coherent superposition of the displacements, that is or the amplitudes. Okay, so it is a coherent superposition of the displacements or amplitudes. So displacements in electromagnetic case, it is the electric field or the magnetic field, that is the displacement. And in case of water, it is the displacement of the water molecule, or in case of sound, it is the displacement of your air molecules. So you have a coherent and what is superposition? I think superposition, you already know that it is a vector sum of, so if you have a displacement, various displacements, so you just add up vectorially at a point all the displacements. So let's say I have displacements y, so the resultant one be the vector sum of all the displacements, and that is my superposition principle. So similarly, you have the superposition of electric field and magnetic field, that you can also write that superposition principle. And another interesting thing which happens here is when this experiment is performed, what we have is a single wave front splits into or divides into two new kind of waves. Okay, so this is known as a division of wavefront. So this kind of interference pattern is known as division of wavefront. Okay, so you have one wavefront which now gets divided into two different sources, virtual sources basically, S1 and S2, and gives rise to new wavefronts, and these wavefronts are interfering. So this is a division of wavefront. Okay, this is what happens in Young's double slit experiment. Okay, so that's why this interference pattern is very unique, one of the unique experiment in physics, and as I said, it is observed for water, sound, and even electrons. Of course, for light as well. So we were discussing about light, but also for electron, protons, and so on. So I think I will then not go into detail just of the mathematics of it, because I guess you know already quite a bit. So just I will describe it briefly. So just to understand it quantitatively in a mathematical formulation. So what you have is, we are saying we have, yes.
Can you repeat that water, proton, and sound one point? What you were saying?
So this the third point.
Yes, sir. Yes, sir.
So I was saying, so you will observe interference in case of water, sound, and also in case of electrons, protons, and so on.
Okay, sir. Okay, sir.
So electron protons also behave like waves. They're like quantum mechanical particles. So though they can behave like particles as well as waves, and therefore they can also produce interference patterns. And electron as a wave is actually used to, if you go in future, probably will into other courses, maybe you will get to know about that. So you also have a electron. You can use electron and make an electron microscope, very similar to your optical microscope. So you can see structures, even atomic structures, using an electron microscope, because in that case the wavelength is very small compared to your light. So light in your visible range, the wavelength is in a few nanometer, few hundred nanometer. But if you use electron, so you can go to really, so depends on the energy of the electron, of course, but you can make it very small, and you can see even atoms using electron microscope. Okay. So there is also X-rays. Also, of course, it is an electromagnetic wave, but you can also use X-rays as well. Okay, so the mathematics is, I think you already must have done this. So the distance, let's say the distance between the sources is D. The distance between the screen is your capital D. And if you want to calculate what is, whether this point P will be a bright or a dark fringe, so it depends on the optical path difference between the light that travels, or the wave travels from S1 to P, and the wave travels from S2 to P. So basically what we want is, we need to calculate the path difference delta, which is your, write as S2P minus S1P. So, and if this delta is equal to integer multiple of lambda, where m is equal to 0, 1, 2, and so on, so you will observe a constructive interference. Okay, and if it is n plus half lambda, so then this is a destructive interference. So that means your phases are opposite, so it will be the phase difference will be pi, and therefore you will observe no intensity there. And you can calculate from this geometry by certain approximation. You can calculate what is delta, which comes out to be 2xn into d in this. So you have xn is the position or the distance of the point P from this point O, let's say. So this is the phase difference, 2xn d. Okay, so if you compare this, so do a little bit of mathematics, which is already given in the book, and you know already. So I'll skip that part. So what you can find out is the fringe width, which is given by the beta, which is nothing but your difference xn plus 1 minus xn, position of, let's say, two bright fringes. Xn plus 1 is one bright fringe, n plus 1th bright fringe, n is the nth bright fringe. So the difference is the fringe width, which will be your lambda d by t. So this is your famous relationship between lambda, the distance between your screen, and the distance between the sources. So this will define your fringe width. And what is the shape of the pattern on the screen? So on the screen, so if I say this is my screen L prime, so what is the shape of the pattern? So normally you observe a straight line, you would say it is a straight line fringes, but they are not straight line. So they are actually hyperbolas when you look at them carefully. So this also you can find out using a bit of performing bit of mathematics here. So if I say this L and L prime represents my xy plane. So this is, I say this is equal to z equal to 0 plane. Then my point P has coordinate. What is the coordinate of point P? That is x, y, and 0. So here this screen is like a two-dimensional screen, right? So but we are just representing it as a one, like a cross section. That's why I have drawn a straight line. But any point on this screen will have a coordinate x, y, 0. And then what will be the coordinate of S1 and S2? S1, the coordinate looking at the system. So S1 will have a coordinate. So this is, and I say this is my, so Z will be anyway minus D because this is the Z is equal to 0 here. So Z is 0 here. So therefore Z, this plane will be, Z will be minus D. The Z coordinate is known. So what is X and Y coordinates? X and Y coordinates will be, so you assume that the X, this is your 0, X is equal to 0 and Y is equal to 0. This is the origin here, the source. So this is a 0, 0. So in that case, S1 will be, so you have to move plus D by 2 to go to S1 and minus D by 2 in X direction to go to S2. So in that case, the coordinates will be D by 2, 0, minus D, and S2 will be minus D by 2, 0, and minus D. So you can again calculate the path difference using this coordinate system. Okay, so if you substitute that, you will get your path difference as well. And if you solve that equation, so I will let you do that. So you will obtain a final expression something like a hyperbola equation which satisfies hyperbola. Okay, where A,
So,
yes.
so the equation of path difference, sir, how it came to 2x and d?
Oh, this is
So does it not depend on the capital D, sir? Distance
it
between the slit
depends,
and the screen.
but what we have assumed, we are assuming that capital D, I mean so we are assuming that D and XN are much smaller than
Smaller
D.
than capital D.
Yes, so this is the assumption here.
Okay.
So since I think you are already aware of this mathematics, so I'm skipping it. But you can have a look, and if you have any confusion, you can ask me in the next class. Okay.
Okay, so thank
But
you.
it is very easy to understand this mathematics. There is no physics here, so that's why I'm skipping. So you can also substitute this, and with some assumption, I mean these derivations are also given in the book. So you can get this equation of your fringes which are satisfy the parabolic, hyperbolic their equation, and therefore they are in fact actually look like hyperbola in principle. But sometimes, I mean, when you look at the central fringes, they look like horizontal straight line fringes, because the locus will be somewhere at infinite. Okay, so that's why it looks straight line. And you can also calculate the intensity at each point. You can at point P, so you can also do that calculation. So here we will use, if we are using the electromagnetic wave, and we say they are traveling in the almost same direction. So one wave is, I say, I cap E01 cosine K S1P. This is my X, okay, or this length K S1P, and E2 vector will be E02 cosine K S2P minus omega T. So since the wavelength is same, so K is the same, but only this path length are different. The X, the value S1P and S2P for both the cases. And I cap is nothing but your unit vector along the direction, the unit vector along the electric field.
And sir, what E1 is representing?
So E1 is so we have two sources, no, E1 and E2. So this is the electric field associated with the wave here, and this is electric field of the electromagnetic wave here, E2. Okay. Another thing, I think, I mean, it is evident, but I should mention that these fringes are very symmetric about your central maxima. So the maximum, so it is really symmetric on the both sides. So since these are electromagnetic waves, so you can represent these wave using this your electromagnetic wave that equation. You can write like that. The solution, or the electric field of the wave associated with the wave, is, you can write like this. And then your intensity, so the total electric field will be, again, this is from your superposition principle. So at any point, E would be your sum of E1 plus E2, vector sum. Okay. And your intensity will be proportional to your E square. That is your modulus of the net or total electric field at any point. That is the intensity. Or I normally will write is like some K E square. So K is your some constant, proportionality constant. So again, the total intensity, you can see again in the book. You can also calculate. This will be coming out to be I1 plus I2 plus 2 I1 I2 cosine delta. And what is a delta? Delta here is the phase difference.
Phase difference.
So this is the phase difference, S2P minus S1. So this is your path difference. This is your phase difference. This is how they are related. You can convert. So if you know the path difference, you can also calculate what is the phase difference and vice versa. So you can then say for a when you have a maxima. So if you have a maximum or you have a constructive interference, so in that case delta will be how much? So some multiple
0.
of 2 pi.
2 pi, yes, sir. Okay, sir. 0
Yes.
multiple.
So I will be equal to I1 plus I2, or rather you will write it as square root of I1 square root of I2 whole square. And the minimum intensity will be
Under root of I1 minus under root of I2
yeah.
whole square.
This is a difference. So therefore, normally you will not. So if I1 is equal to I2, in that case only you will see a completely dark fringe. Otherwise, you will observe some light even when there is a destructive interference as well. And when we say a incoherent light, so this is a coherent light we are talking about. In case of a coherent light, incoherent light, let's say, so if it is an incoherent light, so you were saying that your intensity is equal to I1 plus I2, that is that means there is no interference. So this means there is no interference, and this is because your this cosine delta that you are calculating, you have to average it over, because the delta will be random, because the phase difference, there is no fixed relation between the phase difference. So at each point this delta can vary, and therefore you have to take the average of the cosine delta, and in that case the cosine delta average will be the 0, because it is always it's a random value, and when you average at a point over a time, so this cosine delta will be equal to 0, and that's why your this term, the term that comes here, is only possible if the source or your wave is coherent. If it is not coherent, so this part will be always 0, and you get just a sum I1 plus I2. Okay, so one question I want to ask you. So we are discussing how when this wave interferes, so we said there is a division of the amplitude and there is a distribution of what the intensity, right? So some parts become bright, some parts become dark. So that means there is a distribution in intensity. So what happens to the energy? Any answer? So because these waves, electromagnetic waves, so they carry energy. So what happens to the energy?
So energy is conserved.
Energy is
Sorry,
conserved.
energy is also distributed. Like intensity is power upon area. So power term is represents that energy. So even that is distributed.
Yes. So energy also is there is a distribution of energy as well. So energy is, there is no loss of energy in this process. It is energy still will be conserved, and it is basically it's a redistribution of energy as well. That is what is happening. Good. So I think I wanted to show you some. Yeah, here. So this is like, again, I have taken from the book here so that you can refer to these figures as well. And I have put the figure numbers, if you see here, so figure 14.10. So you can refer to these figures and those sections as well. So on the left hand side, you see this is the hyperbolic nature of the fringe. And then on the right hand side, basically by varying the distance, the screen, no, here what is varying, they are varying the distance between the sources. So small d they are varying. By doing that, so you can actually It appears to be straight line fringes, but ideally they are hyperbolic. Okay. Okay. Another interesting thing which happens. So when we discussed this, so this is from the Ghatak book. Okay, so all these figures and everything what I am showing, all are from the Ghatak book. So now if I change, instead of the sources, I have taken sources along one x-axis, let's say in this case. Now what happens if I put two sources? So let's say my configuration is something like this, S1 and S2, and now I want to see what happens on the screen here. So what do you think? Will there be an interference pattern, and how will it look like?
So circular fringes.
Circular fringes.
Circular
This
Yes,
is a
sir.
circular
rings,
fringe.
rings will be formed.
Yeah. So you will have rings. So I think, yes, I have the figure here. So this is again from the book. So you will have a circular fringes. So now instead of this configuration, so if you have a plane wave and a spherical wave here, so what would happen? So here you have circular.
Amplitude will be increased and on one side and decreased on other.
So will there be an interference or not? If I take a plane wave and combination of plane wave and spherical wave, there will still be interference.
Yes,
Okay,
sir.
so you will see again this circular fringes, very similar to what you see in this case, the first case. You will have again circular fringes. There will be interference. So it doesn't matter whether the wave fronts are spherical or plane. So as long as you have two coherent sources, they will interfere. And the pattern, so the fringe pattern might be different depending on the geometry and so on. But nevertheless, you will always have this interference. Okay, so I will show you one website here. So let me stop sharing this one, and I will share something from the internet here. So you can actually go through that, or let me post that first. That here. So let me post this. So check your chat box. So let's check if you can click on that. So I'm sharing my other screen.
Can please send this link on Google Classroom?
Yes, I will do that. But you can check it now. I want you to have a look now. But I will anyway share and show something here. Okay, so let me share my screen here. Okay. So if you go to that website, it is a very beautiful website. So developed, I think, in Colorado University. So for simulation of these, to look at interference pattern and diffraction, so this kind of experiment. So there are many other simulations you can actually perform. So if you click here, so this is a interactive simulation tool. So let's see if it starts. So it is a little bit slow sometimes. Oh, yeah. Okay. So here you can actually do your own experiment to understand these concepts better. So let's say if I click on interference, then I have slits, I have diffraction. So if I click on interference, let's say, so what you see in the screen is you can choose. So my screen is visible to you?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Yes, sir. So now on the right hand panel, so what you see in the bottom where my mouse is, so you see here you can choose water, sound, or light. Okay. Now to get a light, so you can switch on here. So you can generate the light wave. So if you click again here, it will stop. So here you see the screen size. So this is about 500 nanometer. This is the scale. And this is 1 femtosecond. Like, so this is, so you can switch on the light by clicking here. So then you can change the frequency of the light. So let's say if I go to blue here, red here, so I get red light. So similarly, if I go to blue, so I get blue or violet light. I can change the amplitude of the wave. So this is, then I can change the separation between these two. Okay, so I can change the separation. And then if I click on both, so I will observe the interference pattern. Okay. And I can put here on the right hand panel. So you see if I put a screen, so I will see how the pattern would look like on the screen. Okay, so this is, I have, so you are not able to open it. So you can try maybe later. I will post it in Google
Yes,
Drive.
sir, we can do
You
it.
can try it later. So I'm giving a demonstration of that, so you can use it. It's very interactive, so very nice to use it. So you can try with other buttons as well, what they do. You can also see a intensity. So this is a cross section that we have taken here. So just a line cut. So you see the bright, you have a higher intensity, and for the dark, you have low intensity. You can then change the frequency and see what happens with these patterns.
Yes, sir. The difference between the slits.
Yes, you can change the distance of the separation between the slits. So you can do it for interference. This is a source here we have used. You can use slits. So if you go back, you can see the, so let me start again. So this is a nice interactive way to understand these concepts. So there are many other simulations also available related to physics in this website. So if you are interested, you can also look at those simulations. I mean, it is not only for optics, so they have developed many other this simulation tools. So you can now, for example, choose slits, and now you have, here is a single slit. So you can choose here in the right hand panel here. So if you click here, so you can choose one slit or two slits. Okay. And then again, you can then generate here the wave and do the, so this is a plane wave right now, it's coming out, and you will have a interference pattern. So you can then change the slit width, slit separation. So many things you can do. So have a look at it. It is very useful. Okay.
So what should we do to get that graph that you were?
For the graph, you click here. No, there is a button here, graph. My mouse is there. So do you see that?
Yeah, so it comes parallel to the means.
Oh
So
no,
over
this is a
there.
graph for the. Okay, so this is what we are generating is water wave. So you can choose, let's say, light wave, for example, here. Yes. So here, if I choose the light wave and I choose, let's say, two slits. Now I start with the light, let's say green light. Okay, so I will have an interference pattern. So if I click on screen, so I will see this fringes here. Okay, so when I'm clicking on the screen, so my I see what I would observe on the screen, and then if I click here in the intensity, so you see the intensity pattern. Okay.
Okay, sir. Understood. Yes, sir. Thank you, sir.
Okay, so have a look at it, play with it, so you get a lot of clarification on this. Okay, any questions so far? Okay, so if not, so let's move on then.
Sir,
Yes.
sir, in this there is no equal fringe splits. Sir, why?
No, your voice is not clear.
Sir, fringe's width is not equal in this experiment that you shown before.
Fringe width are not equal.
Yes, sir.
Oh, you can calculate the width. I mean, it will be the same. The not fringe width. Maybe you are talking about the intensity, or
Yes.
the width is same. It will be same.
Intensity changes. Yes, sir.
Intensity changes. Yes, in a double slit experiment, the last one I showed, no?
Yes, sir.
Yes. Yeah, that is because normally you have a, so it is not only a interference that is, so this is because of the geometry, okay, because of the slits. So if you change the slit geometry, it will change. But normally what you have is, so you have an interference term. So the intensity will have an interference term that we just derived, this I1, I2. So this cos square delta term, or delta cos delta dependence. Also, there will be a overlapping of a diffraction kind of effect as well there, because of this geometry. So you will have also another term which will reduce the intensity. So maybe when we go to the diffraction part, so you will understand why the intensity is changing. Okay. So this is normal. Okay. So it is, it happens because you have interference, but you also have, because there is a single slit. So you, although there are two slits, but each slit will also have a diffraction pattern. And this diffraction pattern is overlapped on the interference pattern, and therefore the intensity of this, due to this diffraction nature, so the intensity reduces, okay, from the center.
Yes, sir. I got it. Thank you, sir.
Okay, so let me then share my screen. Any other question?
Yes, sir. Sir, in
Yes.
your screen you said na ki intensity I1 plus I2 means in the coherent case. So why you means, at that same time you said na there is no interference. Can you explain that point?
This one here.
Yes, sir. This one.
Yes. Yeah, I mean, if you have an interference, you will have this extra term that we calculated here. So if it is a coherent beam and there is an interference, so you will have this kind of expression you will get. So if it is I is equal to I1 plus I2, is just a sum of the two intensities. So that means there is no, you don't say there is a interference. So that is what I.
So if they are coherent, they don't have a phase difference, and then we can see that.
Which one?
This one, I1 plus I2, only I1 plus I2.
If there is no, if it is a coherent beam and you are seeing interference, so you will see this kind of, the maximum intensity will be this much. So depends on the phase difference delta. So if the phase difference is exactly 2 pi, yes, you will see I1 plus I2, or I1 plus, yes, you will see I1 plus I2. But if it is, the delta can be, the phase difference may not be exactly equal to 2 pi. So there can be a constant phase relation. So that delta should change the intensity, total intensity. So if, let's say, so you are saying if I have m is equal to 0, let's say, right?
Yes, sir.
So m is equal to 0. So in that case, what will be the intensity here? Sorry. Intensity will be, so cos 0 is 1.
I1 plus I2.
Square root of I1 plus square root of I2 whole square. So that means you have a term, this 2I1 I2, square root of I1 I2, always there. It is not just simple sum of I1 plus I2 for the central, the bright fringe. So when m is equal to 0, So still the intensity will have a component not just simple sum of I1 plus I2. So I1 plus I2 plus one extra term is there. So it is even more compared to your incoherent light, because you have some additional term here. So that's why it is very different from your normal. So when you add the intensity for incoherent light, incoherent sum is different, and when you so this is again comes from the this superposition principle. Okay, so we are not adding the intensity, actually we are adding uh, the electric field. So what we are adding is a electric field. This is a superposition of electric field that is happening at that point. And that now to calculate the intensity, it is basically we are taking the square of that. And since it is a vector sum, it is different from a scalar sum. So if it is a scalar quantity, so then it may not have happened. So you will never get this I1, I2 term for a scalar sum. So when you take the square, no?
Okay, sir. So
The
got
scalar
it.
quantity, you just add up. There will be no interference or anything, because this electric field, which is a vector in nature, so that's why you are getting this kind of uh, interference pattern. So in case of uh, water wave, so we are saying we are adding the displacements. Okay, so displacement is basically it's a vector term. So that's why you see the interference pattern. Okay, so displacement of the water molecule or the air molecule, so that is what we are adding up. So if it is just a scalar term like a temperature or I don't know, any pressure or anything, so it will just add up. So there will be no, you will never see any interference when you take a scalar field, let's say. So this is a vector field, this is electric field, that's why you see this kind of interference. Okay.
Yes, sir.
Okay,
Excuse me,
so
sir.
yes.
Sir, you just explained that different shape of waveforms can also show interference. But
Yes.
for that, sir, the waveforms should be coherent. So if they are coherent, then how can we obtain different waveforms for different shape from a coherent source?
Different wave fronts from a coherent source. That I think you need to do some kind of lenses you have to use, maybe some mirrors, that kind of things you have to use. So you have the same source, and then if you use different mirror settings, so you can get a plane wave, and maybe then you put a pinhole in front of one mirror, so then you get a spherical wave. So
Okay,
that
sir.
is possible. And even
Thank
let's say, so a simple way of looking at it is like if I have let me do that here. So if I have a source far away, so it is, I'm getting a spherical wave. Okay. So now far away, it will be look like a plane wave, right? So if the source is far away, so that is what the sun rays, you assume they are plane wave, because the source is far away from you. So it is a plane wave. So now I can use this as this is one slit where I have the plane wave which is going through, and then I put a pinhole here. So that means I will have a spherical wave here. Okay. So if, the pinhole is basically it's you put a circular hole, right, and that will create your spherical wave. So that is also one way of doing that. So I mean this what I showed. So I don't have any practical example where this is actually used or not. But just to show that this is this interference can happen due to different wave fronts as well. Okay. So I don't have any example of a practical example where it is actually happening in optics. So I can have a look. If I find, I will let you know.
Okay, sir. Thank you, sir.
Okay, so this is using a slit or a pinhole to like that kind of setup, and to get interference is one way of doing that. Is that the only way? It is not. So there is another way of doing that as well. So let's look at here. Maybe I have the example. Yeah. So this is the question: can we obtain this division of wave front? So basically, we are saying there is a division of wave front by a method where we are using slits or pinholes, and we are getting interference pattern. Is this the only way?
No, sir, there are other ways.
So this is
Like
not.
three slits,
So
multiple slits.
sorry, yes.
Sir, we can use multiple slits.
Multiple slits, well, yes, but multiple slits again. We will look at it. This multiple interference maybe later on.
So by
So
prism,
we are just still talking about two slits, like two beams which interfere. So this is one geometry here. So this is known as so constructed by Fresnel. So it's a Fresnel's two mirror arrangement. So Young, he did in the other way. So Fresnel, he said we can do it another way, and he said, so this is the source here. Okay, so let me zoom in. So he said this is the source, and he put two mirrors, M1 and M1, M and M2. So this is one mirror, this is another mirror. Okay, so he put it in such a way, and when these, again, it is coming from the one source and they are getting reflected, so you will observe a interference pattern in this region between B and C. So you'll observe an interference pattern here on the screen, because here in this region only the two waves they interfere. You'll observe an interference, and you can actually see that you have a, so these two reflections create a virtual source S1 and S2. They're not real sources, but they're like almost like a virtual source coming from one mirror and the second mirror, and they interfere, and this is also a possibility. So another possibility which you can also do is using a biprism.
Biprism.
Yes, Fresnel's biprism. So here also you can get a interference pattern from the same source. So let me draw that here. So you have the source here, and then you can create two sources, S1 and S2, all will be in the same plane here. Okay, so then you can also create an interference pattern using that Fresnel biprism. And these kind of constructions were developed actually to calculate the wavelength. So what is the use of this kind of construction or these geometries was to calculate your wavelength of your light, monochromatic light, because you can calculate the fringe width beta using a micrometer scale, and D normally these are well defined, so which you can also calculate using some lens arrangement, and then you can so calculate what is the wavelength of the monochromatic light. So in those earlier days, so Fresnel used this kind of arrangement to calculate that. Okay, so we already discussed about this interference with white light, or let's say sunlight, which has all kind of colors. So in that case, you will all have a central bright fringe, and then maybe a little bit of colored fringe around it. But then later on, when you go farther from the central fringe, so again, because there will be multiple interference, constructive and destructive interference at the same point. So you might also see again a white light as well. Okay, so now let's consider another situation here. This is also very interesting. Let's say if I have the same double slit system here, okay, and now this is S1 and this is S2, and what I do is I put a glass or some other medium in front of this source, so which has a thickness T, and N is the refractive index, and T is the thickness. So what would happen to the fringe? What would happen to the fringes? So what I have done is only introduced another medium, which is, let's say, glass, for example, in front of this source S1, and I want to know what would happen to the fringe. So I will, do I have interference or not? So if I look at this point P, so should I get a interference or not? That is the first question.
Yes, sir, we can get.
We will.
Yes,
Okay, that is, you will observe still an interference pattern because it is still a coherent beam. Only what, by introducing this extra medium, what I am doing is only changing the path length. So I am not changing anything, only this S2P, this delta, S2P minus S1P will be different because there will be additional path length. The light that comes from S1 will travel because of this medium, and this additional path length is, it is N into T. This is the additional optical path length that is introduced in the for the wave that is coming from S1 and going to P. So in that case, what happens, the interference pattern will remain the same, or the fringe or the interference will be there, but only thing is there will be a shift in the fringe pattern because of the shift, this additional optical path length, and this shift normally you can is given by this term N minus 1 divided by D. So the this is the shift, additional shift delta of the fringe. Originally, if you remove this one, so they will, the fringe will go back to their original position, but now there will be a shift, additional shift to this fringes where they were earlier observed. So the central point is not changing, okay. And this is what the shift would look. I mean, this is by the amount which it will shift. So T is the thickness, N is the refractive index. Okay. So you can have a look in the examples in the book 14.10 and 14.11. So these examples they nicely explain how much the shift would be when you use normal visible or like yellow wavelength or green wavelength and so on. But this shift is very small, about a few hundred microns, so about 0.2 centimeter or something like that. Okay, so not much, but you will observe definitely a shift in the fringe. Okay. So all this, when we are discussing about this interference pattern, so one thing I think you should remember that what we need to calculate is the path difference between the two waves they are traveling. So if we know the path difference and then we equate the path difference to the multiple of lambda, or half of the integer multiple of lambda, then we will have a constructive interference, otherwise a destructive interference. So any geometry, if you are given in this kind of interference problem, so if you can calculate what is the path difference, so then you can calculate the condition for maximum and minimum. Okay, so this is we talked about this interference due to division of the wavefront. So there is another thing that which can also happen when a wave interacts or meets another medium. Okay, so let's look at that. So I told in the beginning, in the first class, so if I have a medium here, okay, so light comes, there is incident light here, so I will have a reflected light, and then so maybe this is your refracted or transmitted light. Okay, so this is you either call it a refracted one or transmitted one. So this is what you will have. But the situation will change if I take a very thin film. Okay, yes, so if I take a thin film, let's do that. So this is a thin film. So normally in a thin film, in the optical sense, we would say the thickness is of the order of few micron. So maybe 5 micron, 5 micrometer, or 10 micrometer, or even like between that range. So this is typically the thickness we would assume. So what happens when light falls here? So of course there will be first one reflection will be there. So there is a refraction, and this is again another refraction will happen. But we will also have a reflected partial reflection here from this surface, and then there will be also another refracted wave from this direction. So you can have actually even multiple reflection and refraction and so on of the same light beam. It can go through multiple of these things. So what is happening in this process? Okay, so you can also have, so now this light which is coming out on this side, so you will have, let's say, multiple of that. Okay, so on. So you can have an interference here of this light as well. Okay, so this is another way of observing interference pattern. So this is known as interference by division of amplitude. So what we are doing fundamentally here is dividing the amplitude. So in the earlier case, there was no change in amplitude, only dividing the wavefront. But here we are dividing the amplitude. So we are still keeping the source coherent, everything is same, but we are only dividing the amplitude. So why there is a division of amplitude? Because of this reflection, partial reflection and partial transmission. So how one can calculate how much is reflected? So normally it depends on the coefficient of reflection and coefficient of transmission. Are you aware of these terms?
Yes, sir.
Yes. Okay, so that's good. So if I have a incident amplitude A, and the coefficient of reflection is R, so how much will be reflected then? So reflected amplitude will be
into R.
A into R.
Yes.
Or R into A or A into R, right? So similarly, if T is my coefficient of transmission, So I am not saying transmission is due to refraction or any other process. So I'm just saying it is a transmission. So then the transmitted amplitude is A into T.
So A into T or A into 1 minus R also we can write now.
Yes. So ideally, what you have is A should be equal to AR plus A into T. So that means your R plus T should be equal to 1. So if you know R, so you can calculate T, or if you know T, you can calculate R. So if I have R is equal to 1, that means I have a 100% deflection. So if R is 1, so all the wave that is falling on the surface is getting reflected. So that is 100% reflection. Or similarly, if T is equal to 1, so nothing will be reflected, all will be transmitted. So here, one thing which in this context people talk about in physics, they follow this light ray. When they travel, they follow something known as a time reversal invariance, or the equivalent name is optical irreversibility, or optical reversibility here. So not irreversibility, but reversibility. So that means if I now take this, change the direction of propagation of light. So instead of saying this is incident on this and going like this, so if I say and the light is incident like this, so it should follow back the same path. So there should not be any change in that. So that is the optical reversibility, or in a mathematical way, we call it, it follows the time reversal invariance. Okay, so this is a very basic principle that is applicable to many fields in physics, particularly in optics. So you can have a look at this term if you want to know more about it, but I will not discuss that more here. So let's look at this, how we can create this interference pattern, and whether it is really useful or not. So one way we saw, we can create this double slit and so on. So we look at many of the fundamental behavior of particles in using that experiment, and that's why that experiment is very useful in physics, very important in physics. But in terms of the engineering application, there is not much. But this kind of interference has a lot of engineering applications. Okay, so when you do an interference by division of amplitude. So let's first look at some of the fundamental things, what we mean and what is the condition of the interference. So before going into that, so one thing, when the light is falling on this thin film medium, so what is happening? There is a division of amplitude. So one thing is, say, division of amplitude. And another thing also can happen. What is that? That is a change in phase of the wave. So it is also again a very general, so it can happen to all the waves, mechanical wave or even this light wave as well. So when a light falls from a rarer medium onto a denser medium, so this is your N1, this is your N2. When N1 is less than your N2, so that means light is coming from your rarer medium to a denser medium. Okay, so that is we call, so N2 is a denser medium because the refractive index is high. So when light is reflected in this case, so there will be a phase change pi.
Yes, sir.
So a phase change will happen. The phase change is a pi or lambda by 2 path change, that is equivalent to lambda by 2 change, path length will change. Okay. And if on the other way, if the light is coming from a denser to a rarer medium, there will be no phase change. Okay, so the phase change will only occur when there is it's coming from a rarer to a denser medium. So these two things happen. Then how this affects your interference? So let's look at a very simple example here. So I take a thin film material with a thickness D. Okay. Now I have an incident light. So I am assuming it is a normal incident. So what would happen? So light will be reflected from the top surface. So there will be a reflection here. There will also be reflection from the bottom surface, because this light will also partially get reflected from the bottom surface. So now these red and black ones, they will interfere. So this is, we are keeping it simple just to understand the physics of it. So in order to know the condition for the interference, so we need to calculate the path difference. So what is the path difference? When this blue and the path difference between the blue and the black one. So the path difference delta will be nothing but n d. So this is the optical path that
Less lambda by 2.
The blue one will travel twice n of d. So n is your refractive index. So this is the extra path length this black light will travel, and then it will come out from your thin film medium. So this is the path difference. And now if I want to look at the condition for the maxima or minima or the interference, so what would be? So here you have to be careful a little bit. So the condition for maxima is when this is your or constructive interference. So earlier we used to say it is just multiple of m lambda. So m is again your integer. So now it is reversed. Why? Because the red one will undergo a additional phase change pi, or a path change. There will be a lambda by 2. So that's why this condition is reversed. So similarly, for a minima or destructive interference, this path difference should be equal to m lambda. So that is your minima, or let me say destructive interference. So this is a slight change in the condition of interference that we saw earlier. Okay, and this is due to this additional phase change that is introduced when there is a reflection from the top surface. Now, what would happen? So before going into this application, so what would happen? So let's say if I take a medium 1, or the same medium I have, let's say this is my glass, this is also glass, and I have air here. So it is like I have created a air film, thin film of air between two glass plates, let's say. So what do you think would happen to the condition of interference? What do you think? So I will give 3 examples. So, and give you a couple of minutes to think about it. So this is one case. Another case I have glass, I have oil film. So I will also mention. So here n is equal to 1. Here glass is n is equal to 1.5. Here for oil film n is equal to 1.6. This is again glass is 1.5. And the third situation is I have a oil film here, but I have another glass here. So here n is equal to 1.5, here n is equal to 1.6, and here n is equal to 1.67, let's say. So I have 3 different situations. So what do you think would be the condition for interference in these 3 cases? So think a little bit, couple of minutes, and answer. So you can answer with the first one if you know already. Is the question clear?
Yes, sir.
Yes. Okay.
So first one is possible, sir.
So what is the condition for interference? What do you think?
Sir, the glass have more refractive index than air, sir. So we can write here delta x equals to.
So if I say this path difference, and I want to write
2m plus 1.
So let's say, what is it, a constructive interference or a destructive one?
Destructive.
Destructive. Okay. Everyone agrees? Or is it different for others? Okay, so I will leave this problem to you, and I will get an answer from you in the next class. So this is we will start with this in the next class then. So let's go to the next topic. So the problem is clear, so you can think about it and write down the condition for interference in all the 3 cases, because this will give you a idea how this can be actually applied for some application. So we will talk about some applications in the next class. So before that, I want to consider another condition for the interference. Yes, assume all are 0, angle of incidence is 0. So it is a perpendicular incidence. Okay, so light always falling perpendicular to the surface. So if I take, instead of assuming a perpendicular incidence, so let's say I have an oblique incidence. So what would happen if I have that condition? So now I have a thin film where now light is incident at angle. So in this case, we say this is the angle theta. So this is theta prime. Sorry. So what is the path difference in this case? So again, this is a this is a oblique incidence. So the path difference you can also calculate by geometric consideration. So in a way, so if I say this is so I want to calculate the path, the extra path between this wave, right? This is the oblique incidence. So extra path traveled by this one is, so let's say this point is B, this is, I say, D, this point is F, and then I put a perpendicular one here that I call C. So I can calculate the path difference between two rays, so which will be equal to, so delta will be equal to BT plus DF minus B. Okay, so the wave which is represented by this one this one, so this is the blue one, which is the normal reflected light. Okay, so what is the path difference between the blue and the red one? So it is BD DF minus BC. Okay, so what is BD? So here the thickness is D.
D sec theta dash BD.
Sorry?
BD is D sec theta dash.
So the optical path length you can write. So this is only the writing. We are writing the actual length, but there is to be a optical path length. So which we should introduce this refractive index. So which I say N into BD or N2. So if I say this is N2 refractive index, and the refractive index is N2, in that case I should write something like N2 DF minus N1. Okay, so this is the actual path difference. And if you do the look at the geometry and do the calculations, so you will get an answer which is equal to 2N2D cosine theta prime. So theta prime is your angle of refraction. So you can do the calculation and find it out. So y delta is equal to 2N2D cosine theta prime. And the condition for your interference would be, so this is not going to change, so it will be again m lambda will be your destructive one, and m plus half lambda for constructive. Okay, so this is your condition for interference. Only thing, the path difference has been changed. So earlier it was just 2ND because there is no oblique incidence of theta was involved, but due to this involvement of cosine theta, there is so the path length has changed, and this condition, this delta is equal to 2N2D cosine theta prime, is known as, this is known as a cosine law. Okay, so sometimes it is known as a cosine law. Okay, so we will actually consider some of these applications of this interference pattern for some application in the next class. So we will start with the discussion, or do you have an answer to this question? Any of these questions already?
No, sir.
Okay, so have a look. You can look in internet or in the book. In the book, of course, it is given. So you can look it up, and then we will start with this discussion, and then go to how this is useful in some application. We will look at that. So this interference pattern by division of amplitude. So we encounter two interference two ways you can perform interference. One is by division of wave front. So that is the classic example of Young's double slit experiment, or you take a mirror arrangement, the biprism or any other mirror arrangement. And the second one is the division by amplitude. And we will see some of those applications, how that is useful, these concepts useful in engineering applications. Okay, any question?
No, sir.
No?
No, sir.
No, sir.
Okay. If no more questions, so then we
Sir.
will stop. Yes.
Sir, please post those solutions for example 11.5 and 11.6 and 11.9.
Which
you
okay.
gave in the previous
Yeah.
class.
Yeah. Okay. Sure.
So because in book I was not able to understand the book's language, sir, in your language if you can provide.
Okay. So the solutions to those examples.
Yes, yes.
Okay. Sure. Okay. Okay. Anything else? If not,
No,
so
sir.
then yeah, we'll stop then.
No,
We'll
sir.
meet again tomorrow at 11. Thank you.
Thanks.
Okay. Thank you, sir. Bye,
Thank you,
sir.
sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank
Thank
you,
you,
sir.